Good morning. This is Michael Dong on episode number 6, acetonitrile versus methanol. Which one is a better mobile phase for reverse phase of pharmaceutical analysis? Scope. There is a perennial argument whether methanol is better than acetonitrile. The dispute started in 2008 during an acute shortage of acetonitrile when prices escalated. To date, the price of a gallon of HPLC grade acetonitrile is about 2 to 3 times higher than that of methanol. Here in this episode, there are some pros and cons from a wider perspective, from the physicochemical properties of both solvents and also the chromatographic attributes. A summary of physicochemical property: a methanol with a structure and acetonitrile with a structure. Note that methanol is a proton acceptor and also a donor. It can hydrogen bond, while acetonitrile is an aprotic solvent without any ionizable hydrogen. It's primarily a proton acceptor. However, it can do pi-pi interaction. From the boiling point view, methanol boiling point is 65 degrees C, while acetonitrile is less volatile at 82 degrees centigrade, which is somewhat better from the toxicity point of view on inhalation risk. And also, acetonitrile is somewhat less acute toxicity as that of methanol. From the viscosity point of view, methanol viscosity is 0.54 centipoise, while the viscosity of acetonitrile is significantly lower at 0.37. Now, these have implication in terms of flow rate, where acetonitrile can support higher flow rate, and also in terms of column efficiency. Finally, the UV cutoff of methanol is 204, while acetonitrile is much lower, so acetonitrile can support higher sensitivity at far UV detection. So in these aspects, the acetonitrile appears to be superior from the physicochemical properties point of view. Next is the chromatographic attribute point of view. And here is the quite famous selectivity triangle, where we have the three primary mobile phase B or organic phases used in reverse phase liquid chromatography, starting with methanol, acetonitrile, and also THF, tetrahydrofuran, and showing their position, relative position in terms of the chemical property in terms of proton acceptor, proton donor, and dipole interaction. As mentioned earlier, methanol can do hydrogen bond and somewhat much better in terms of separation, isomeric separation. So methanol have a little advantage on selectivity for isomeric separation. We mentioned the solvent strength point of view chromographically. According to the Hildebrand scale for normal phase chromatography, the methanol has a strength of 0.95, while the Hildebrand scale for acetonitrile is lower. Since reverse phase is the opposite of normal phase, acetonitrile is a much stronger solvent for reverse phase chromatography. In terms of viscosity, we mentioned that the acetonitrile is lower and therefore support better column efficiency from both the ability to go to higher flow rate and also from the mass transfer advantage, which we would talk about later, that give acetonitrile a slight edge in terms of column efficiency. I think the UV cutoff is pretty significant where acetonitrile can go down all the way to 190 and therefore support a more universal UV detection even at 190 when paired with a transparent mobile phase A. Want to mention the on the reverse phase illuminate the allotropic strength. Acetonitrile was higher than THF is higher than acetonitrile, which is higher than methanol and much, much higher than water under the reverse phase condition. Here's a case study supporting some of the statement we said earlier, comparing the use of mobile phase B of methanol versus acetonitrile. The operating condition is shown here using a water select charge server hybrid C18 of this dimension. These are the mobile phase A and B. B is either methanol or acetonitrile methanol in the upper chromatogram and acetonitrile in the lower chromatogram. And the gradient condition from full gradient from 5 to 95% B in about 8 minutes at this flow rate, showing the separation of 12 acidic, basic, and neutral pharmaceutical component here. Here is some observation. One can see that if you compare the elution profile, the profile is intact between methanol and acetonitrile because in both cases, the retention mechanism is primarily hydrophobic interaction. However, acetonitrile has faster analysis time because it has a higher allotropic strength in reverse phase. So you can see that acetonitrile elute the peaks much faster with lower retention time. And also because it's stronger solvent, it can support the elution of more hydrophobic drugs or hydrophobic solutes, making it the ability to support a little wider gradient range. Second, acetonitrile support higher flow rate because of its much lower viscosity, particularly when mixed with water. The viscosity with a mixture of methanol and water is actually much higher than water, as much as 1.5 at 50% methanol water. So the pressure would goes up during the middle of the gradient, while acetonitrile are much lower. Therefore, it can run a much higher flow, which is advantageous for gradient elution because you can push out at higher flow rate a larger gradient volume throughout the method. Also, the lower viscosity of acetonitrile actually give an advantage from the column's efficiency point of view. Typically, one finds that the efficiency under isocratic condition is roughly about 10% better in acetonitrile. That is because of the higher solute diffusivity under the mobile phase. This term D sub M is bigger for acetonitrile. Therefore, the Van Demeter C term, the Van Demeter equation here with A, B, and C term, is significantly lower for acetonitrile, giving a higher column efficiency because it supports a lower plate height under the same condition. So here's the third bullet point. Acetonitrile had to use higher column efficiency or plate count N, or in terms of peak capacity, because of the lower viscosity, leading to a lower Van Demeter C term from higher solute or the analyte diffusivity in the mobile phase. In case study 2, we document the separation of diastereomer of an NCE, a new chemical entity with 3 chiral center. Here is structure of the NCE, new chemical entity. which have 3 chiral centers. And therefore, the total number of diastereomers is 8. And with a good method, one have the possibility of separating the 4 pair of enantiomer from the 8 diastereomer. As shown here is 2 methods. One is using acetonitrile under a very similar pH condition. And you can see that for acetonitrile, separation is pretty good, but not based on resolve. In the bottom chromatogram, we actually we do have use a different column using a phenol column, a couple of methanol, and in this case, methanol give baseline separation of 4 pair diastereomer. So in general, for isomeric separation, particularly for diastereomer, methanol is better because of the ability to hydrogen bond and also the ability to have polar-polar interaction. So methanol, in general, tend to have higher selectivity factor for isomeric separation due to hydrogen bonding and polar interaction. Now, this is particularly significant under the nonpolar chiral separation condition, where methanol and isopropanol is always the preferred modifier for hexane. We want to switch gear and talk about the use of the solvent as a final solvent, final sample diluent. I want to point out that default sample diluent for anything unknown, particularly in drug discovery samples, is 50% acetonitrile with water without any acid or base. So this is kind of default sample diluent when the solubility of the sample is not known. The use of methanol as a sample diluent is highly discouraged because of its ability and propensity for esterification with carboxylic acid to form esters. So definitely it's really a no-no to use methanol for drugs because any acidic functionality might esterify and form an equilibrium with esterification. So as a sample diluent, ACN tend to be more inert. It's preferred because it's a proctic solvent. And also it has a higher solubility for more hydrophobic drugs. How about in the case of HPLC? HPLC stands for hydrophilic interaction liquid chromatography, which is a emergent mode, which is becoming popular for its separation of polar aniline and polar drugs. Now here, methanol is rarely used as a primary organic solvent in HPLC because it tends to disrupt the water-rich layer, which is required in HPLC on the stationary phase. It also weakened the retention of polar aniline, and particularly bothersome is it alters selectivity in a way which is highly unpredictable. So for HPLC, acetonitrile is the preferred mobile phase since it supports better the partitioning mechanism central to HPLC, where there are several layers of water adhering to the polar support. So here are my final conclusion. Which solvent is better? I would say the better is under quotation. The conclusion that I can draw is the fact that while methanol is less expensive and also less susceptible to market shortages, acetonitrile is the clear winner as the preferred mobile phase B in reverse phase because of its superior physicochemical and chromatographic property, leading to higher strength and higher column efficiency and better for far UV detection at low wavelength below 210 nanometers. So here's my choice, personal choice for mobile phase B. in the reverse phase method development, and I always start with acetonitrile, and I always use acetonitrile as my sample diluent if I can. Here are some references, starting with Snyder, Kirkland, and John Dolan's book, Introduction to Modern Liquid Chromatography, my own book, HPLC and UHPLC for Vaccine Scientists, and I'd like to recommend this particular white paper written and published in 2018 between myself and Barry Boyle of AMT, which is one of the better white papers on modern trends and best practices in mobile phase selection in reverse phase chromatography, where we talk about both selection in mobile phase B and also mobile phase A. And finally, some YouTube channels on HPLC Fundamental, particularly episode 4 and 5, and also Pharmaceutical Analysis Series, episode 2 and episode 4. On this note, I'd like to thank you for listening to episode 6, acetonitrile versus methanol, which one is better, and I have clearly defined my preference as acetonitrile as a starting mobile phase B in method development. I encourage you once again to subscribe to the channel, and we thank LCGC Magazine as a channel collaborator. See you next time. Bye bye.